Let me start. So hello everyone. Today I'll present my research on cooling efficiency of thermal power plant and thermal pollution on global rivers in warmer climate. First of all, I would like to thank Okuda-kun and Chang for helping me to make this poster, and I would like to thank Oki-sensei, Hyunjung-sensei, and Tokuda-san for their consistent support. Also, I would like to thank JICA and Sutra for their financial support. So climate change is influencing the global water cycle, and the global warming is causing the water temperature to rise in rivers. Now, the power plants need tremendous amount of water to cool the steam in the steam cycle, and this will be affected by climate change. In the future, such changes are anticipated to intensify. In this study, we determine how much is the water availability that is discharged here in the rivers is changing, how the water temperature is being affected in the future, and how these effects on water temperature and river flow are affecting the power generation in the thermal power plants and the thermal pollution so caused by them. So here we can see some modeling framework for the study, and more detail will be given in the discussion session if you want to. But climate change would increase the water temperature and decrease the water availability for these power plants, and in turn increase the water withdrawal and the return flow and the effluent water temperature in the future. So the new power plant model, enabled power plant model, predicts the water temperature in a much better manner in comparison to one without the power plant. The blue dots are here without the power plant, and the red ones are with the power plant, and we can see that the accuracy is higher in case of the red dots. So next thing is the water temperature rise due to power plants. Here we have shown it for the historical scenario, which is the near past, that is 1985 to 2014 average. And we can see that the water temperature rises in the region where there are a lot of power plants in the upstream regions. And the water temperature can go as high as 3 degrees Celsius. In fact, in certain cases, a water temperature rise of more than 10 degrees Celsius has been reported in certain situations. So the next thing is the main results, which is here. Here we see that the water availability, that is discharge in our case, is changing in the future. We have shown 4 possible futures with global temperature rise of 1.5 degree, 2.5 degree, 3.5 degree, and 4.5 degrees Celsius at the end of the century. We can see that at the location of the power plant, there is a decline in the water availability in most of the scenarios, but in certain future scenarios such as SSP 370, or where the global water temperature, global air temperature is about uh, uh, 3.5 degrees Celsius, the water availability increases. This figure here shows the red regions with declining water availability and blue regions with increasing water availability. However, in case of the global, in case of the water temperature, this is not the case. It's always increasing with the air temperature increase, and there's a continuous intensification with increasing climate change in the future. So here we next we predict the production efficiency by using our power plant model, and production efficiency is computed as the power production by generation capacity, and we can see that the production efficiency tends to decline for once through cooling system and combined cooling system. Once through cooling system and combined cooling system are two types of cooling system, which again can be discussed later for details. But we can see that for both of these cooling system, we can see a decline in the production of power or the production efficiency in this case. Also, the water temperature rises due to the power plants in most cases, and which can be seen consistently increasing for the once through cooling system, that is in blue color here. However, for the combined cooling system, due to the policy constraint, we can see a decline in the water temperature rise due to the power plants in the future. So if you want to have more details, please let me know in the discussion session. Thank you very much.
Hello everyone and welcome. My name is Xizhou Huang, third-year doctoral student from Moki Lab. And today I would like to share with you a little bit about the surface water eutrophication and estimation of the total amount of phytoplankton from land to sea in the late 20th century. I'll first introduce some background. Discharging the anthropogenic pollutions into water bodies into water bodies is one of the biggest water-related problems. Population, crop production, and economic development produce million tons of nutrients in recent decades. The global hydrological cycle has also transformed greatly by human activities. The harmful algae blooming is then occurring in surface water due to the excess of nutrients input and the change of hydrological cycle. And the people call it eutrophication. Phytoplankton is one of the most common reasons for water quality damage and the eutrophication in both freshwater and seawaters. However, the total amount of phytoplankton from land to sea has not been understood thoroughly. So in this study, we proposed an integrated model assessment from incorporating several validated models, including a land surface model, Masashiro, a terrestrial nitrogen cycle model, and a set of coupling model of riverine hydrodynamic model, Camouflage, the river temperature model, Heatlink, and the global water quality model, Meteor, along with necessary external data, including the atmospheric forcing and organic and inorganic nitrogen and phosphorus, plus organic carbon. The enhanced version of nitrogen cycle model dealing with the nitrogen fertilizer, manure, atmospheric deposition, municipal wastewater, and aquaculture pollutions input, and the water quality model involves 10 different in-stream processes here, including the photosynthesis, respiration, mortality, nitrification, denitrification, settling, reaeration, decomposition, oxidation, and hydrolysis. So the result, it is found that the average yearly export of global phytoplankton in the 1970s was about 21 teragram per year, and to the 26 teragram per year in late 1990s, which is increased by 21% for 30 years past. From the hotspot that phytoplankton reaching to the river mouths, we can see that Asia and Europe contributed most on forming and transporting the phytoplankton. Also, on the upper right figure, it is very clear that the Asia dominated the share of the phytoplankton export to sea during the late 20th century with over 12 teragram per year in 2000, followed by the Europe is around 6 teragram per year. North America and South America have similar share of 3.5 teragram per year, and Oceania has lowest 0.4 teragram export per year. And interestingly, only Africa shows a decreasing trend from 0.9 teragram export during the early 1970s and 0.75 teragram export in 2000. So the conclusion and outlooks for this research is that first, the increase of nutrients, especially nitrate, nitrogen, and phosphate, phosphorus, have greatly influenced the forming and the export of the phytoplankton. And second, the result from this study can be good indicator for policymakers under the stress of the eutrophication. And lastly, future scenarios, including the change in climate, the population, and GDP can be imported into this model for making the prediction of future eutrophication and the water quality trend. So if you have any questions, welcome to contact me. Thank you.
Good afternoon, everybody. My name is Chengyao Zhang, D2 student under the supervision of Professor Oki. My research is focusing on water resource management in large river basin. As we know, with the development of social economy and the population growth, as well as the limited supply of available water resources, competitions between different water sectors are exacerbated. Solving the issue of water scarcity relies not only on the availability of water supplies, but also on rational and effective management and allocation. The target area is Yellow River Basin in China, spanning parts of 9 provinces. It is one of the areas which face the most significant water shortage problems. Water use competitions are intensified among different sectors. Therefore, the limited available water should be managed efficiently to maintain the sustainable development. And the lower reaches experienced the river cutoff continuously as a result of excessive development by humans in the late 1990s. Therefore, both the ecological environment and human water uses are supposed to be highly concerned when implementing rational water allocation. And water serves for different sectors and can create different values. Valuing water can potentially lead to better decision-making for water allocation and management. Therefore, this study aims to answer three questions. How much economic benefits can be produced by water inputs for agriculture, industrial, domestic, public, and urban ecological water sectors, and at least how much environmental base flow should be maintained in the river channel, and what is the optimal water allocation scheme among 5 sectors in the river basin. So this study first built a comprehensive evaluation framework to assess the value of 5 sectors. For agriculture, industry, public, this study built the Cobb-Douglas production function for each sector, and the economic value can be of United Water for these sectors are estimated by isolating the marginal contribution of water to the total output value. For domestic water sector, the value can be assessed by the people's willingness to pay for domestic sector. And the approach to build a power demand function for household, and the value can be estimated by the economic surplus of the demand function. And for ecological water sector, because it is used for irrigating the green land in cities, so the value could be considered assessed by the ecological service function of green space. And the main functions include the water conservation, gas regulation, cooling, and so on. So the methods of estimating these values mainly include the replacement cost and the shadow engineering method. About the water allocation model, the Nash-Hassanian bargaining game theory is adopted as the basis of this study to allocate water among 5 sectors. It is a cooperative game to find win-win solutions. The objective function is to maximize the product of the ground coalition members' additional utilities compared to the non-cooperation cases using bargaining and cooperation. And the monthly neutralized flow and environmental based flow of lower reaches were assessed by integrating the HOE model's monthly seasonal pattern of agricultural water withdrawal. About the results, the estimated economic benefits produced by 5 sectors are shown in these 3 figures. And the annual environmental base flow is 7.5 billion cubic meters a year. And the optimal among 5 sectors, annual allocations for 5 sectors is shown in this figure. The estimated value of agriculture, industrial, domestic, public, and urban ecological water use sectors are about 34, 4.6, 1.8, and 2 billion cubic meters, respectively. Yes, if you have any questions, please communicate with me. Yes.
Welcome to my post, and my name is Menaka Revel, and from Yamasaki Laboratory, I'm a postdoc here. So our study is about developing a framework for the global discharge estimation using satellite altimetry. So as you may know, like in our group, mostly we are using computer models to predict the water, global water. And with the recent advancement of the satellite data, we can combine both the satellite as well as the computers to predict the real dynamics of the rivers and the water. So in this study, we are kind of thinking about how effective the combination of the satellite altimetry with the computer models to in improving the discharge estimation. So in this study, we are focused on a satellite mission called Surface Water and Ocean Topography mission, which have 1 day to 3 year span of temporal span, and it can measure these surface waters. And some of the characteristics of this mission is given here, such as altitude and the most importantly the repeat days is around like 21 days. So it goes through a particular point every 21 days time. And we have used a method called data simulation here. In data simulation, we have forecasted values using the model in green color here, and the truth observations in the blue stars. And we combine these two model predicted values as well as the truth of measurements of the observations in order to get a more correct value shown in red square here. And we kind of try to correct the model forecast using the observations we have in the real time, and we try to improve our model forecast. So in this method, we have used empirical patch, which is called as empirical local patch, which we use the area of some particular area to get the observations. For example, in this figure, the blue color area is used to assimilate the observations in that area for the red star mark. So by doing so, we can limit the errors due to the observation sparseness in the temporal and the spatial scales. And by combining these local empirical patches with the data simulation method, we could be able to improve the river discharge, mostly in the large rivers such as Amazon. So in this figure shows a hydrograph for the Amazon river, and the blue color line is the predictions without assimilation, without using the satellite observations, and the red line shows the assimilated value, and the true value is underneath this red curve, which is in black. So we can see mostly the assimilated river discharge is very much represent the true values of peak discharge, peak timing, and the low flow conditions as well. So the right hand side global map shows how efficient our assimilation system is, and if you can see the green color, that means the assimilation is good. If it is brown, it is not very good. So we can see mostly in the highlighted regions as well as the large rivers, the assimilations performed well, and in upstreams or the small scale rivers, the assimilation not performed well. So we found that where can be the data assimilation can be effective for estimating river discharge estimations correctly. Thank you very much. If you have any questions, please feel free to contact me.
Good afternoon, everyone. I am Prakat Modi, doctoral second year student of Yamazaki Lab. So today I would like to talk about my research topic, multivariable integrated evaluation of hydrodynamic model, a comparison of performance considering different baseline topography data. So the flood model, which is like hydrodynamic model, depends on many input data like runoff and topography, but the accuracy of the model is important since its application in various fields like flood monitoring, risk assessment, and climate impact assessment. But the performance is evaluated mainly based on the comparison of output from the model and the observations that are collected. Previously, most of the researchers, they did the comparison based on the discharge data, that is the river flow data. But now, due to the advancement in the technology, satellite data such as water surface elevation or water level and flood extents are available, which help us to increase the accuracy assessment performance by considering them in the evaluation. As we know, like the models having different parameters, and if we will judge the model performance accuracy just by the single variable, there are chances like we will never achieve the we will never get to know how well the model is performing based on the single variable, since there are multiple chances like the many parameter sets can give the same value. But if we'll consider the multiple variables, they are less probable that same value of discharge, water level, and flood extent combination will give the same evaluation. So the consideration of multiple variables can give the more confidence about the assessment of the model. But at the same time, we use different evaluation metrics for different variables, and also the different variables have different spatial and temporal resolutions and unit of measurements. So combining them is like little difficult, but in our research we try to achieve this this objective of combining the different variable evaluation. So here we have used the Kamaflood river hydrodynamic model, and the data set used is like runoff forcing as an input data, and discharge, water surface elevation, and flooded area has been used for the evaluation comparison. We have used two topographical data, which is digital elevation model from SRTM and MERIT. So we assume like since MERIT is advanced produced using SRTM by removing the biases, we assume it can represent better altitude and slope, and it can perform better, and it can increase the accuracy in all the three variables, that is discharge, water surface elevation, and flooded area. The model parameterization here, we use like we perturb the river depth by changing the river depth at mouth and changing the gradient across the basin. And the river depth is basically given by very empirical formula, which is h is equals to a q to the power b, and where a and b are constant. So we change the a and b constant to get the different ranges of parameters. To combine the different variables evaluation, we taken Amazon basin as our study area. We divided the Amazon basin into 25 different regions, such as for both the topographic data or each subbasin having similar areas, and only the data for the main streams of the subbasins, as you can see in yellow and red colors, consider for the evaluation, especially for discharge and water surface elevation. And the pink color is the flood extent around the zones of 50 kilometers buffer zone of the rivers has been considered to for the evaluation, to exclude the permanent water bodies like lakes and other things. The one matrix called overall basin skill score, OSK, has been uh, implemented. Here we have used normalized net surcliff efficiency to compute the OSK for each subbasins, and the best parameter has been considered, which is having parameter with the highest OSK values. We found that the Kamaflood performed well with the MERIT DM topography data compared to SRDM for a range of parameters, and also the time series performance for MERIT DM is either as good as SRTM or better than the SRTM DM. But we can see we found that the water surface elevation for MERIT DM is much better than SRTM. It can be because since the digital elevation model, that is the topographic data, directly affect the water levels. So as the conclusion, we can say like this OSK matrix can be used for calibration and evaluation of model, and it can give the a robust evaluation considering different variables. Thank you. For further information, you can join the discussion session.
Okay. Hello, everyone. My name is Ricky Lee, and I'm a master's student under the supervisor of Yamazaki Sensei with the help of Shidong and Watanabe-san. And my research topic is attribution of extreme precipitation events in Japan to climate change and climate internal variability. For the background part, Japan suffers from extreme precipitation a lot for recent years. There are already a lot of research trying to attribute these extreme events to global warming. However, number of extreme precipitation in Japan shows some high values in the past, and it has large year-to-year variance. And this may be explained by natural variability. Therefore, this research studied the impact of internal variability on the occurrence of extreme precipitation in Japan and the role of climate change plays in the occurrence of extreme precipitation and the comparison between the impacts of both of them. The database I'm going to use is D4PDF. For AGCM experiments, each set has 100 ensemble members for which the initial conditions and the lower boundary conditions are perturbed. Its large-scale pattern is identical among all ensemble members, while noises corresponding to the observation or uncertainty are added. In the climate variability section to have a general look. The left figure shows the Pearson correlation coefficient between number of one-day 20-year return period extreme precipitation in Japan each year, and the SST in June, July, August each year. You can see that Pacific Ocean and Indian Ocean have a relatively high correlation coefficient. So I chose ENSO as a starting point to build a research structure, and it is defined by ONI index, which is 3 months running mean of sea surface temperature anomalies in region Nino 3.4, based on 30-year average of the 3 most recent complete decades. And the middle figure shows the Spearman correlation coefficient between number of extreme precipitation events in each year and ONI when it could give the largest correlation. A blue curve is for non-warming scenario, which teases out the influence of global warming and focus on internal variabilities. A red curve is for historical scenario. This is to see if the correlation found in non-warming scenarios still exists. We could see that large Spearman correlation coefficients with high significant level, so that warm SST anomaly in equatorial Pacific may increase the likelihood of occurrence of extreme precipitation in Japan. To have a closer look of the more detailed ONI group, the probability density of ONI index when extreme events occur, and the probability density of ONI index in the whole period are compared in the right figure. We can see that positive ONI is more likely to have simultaneous large-scale extreme precipitation in eastern Japan. And in the second part, I studied the impact of climate change on one-day extreme precipitation in Japan. Left figure shows difference of extreme precipitation intensity between historical and non-warming scenario calculated by historical minus non-warming. So climate change increases the intensity of extreme precipitation in Japan for most pixels. And from the FAR value in the table, we could clearly see an increasing trend from 1951 to 2010 that the climate change has enhancing the extreme precipitation. And further study would be made based on regression analysis to compare the importance of the two factors, which is not shown in the poster today. And that's all for my presentation today. Thank you for your listening.
Hello, everyone. Sorry for the internet error. And I'm Shudong Zhou from Yamazaki Lab. I'm now a special appointed assistant professor, and this work is about uncertainty of flood frequency analysis in hydrodynamic model simulations. And thanks Masan and Yamazaki-sensei for the support. So flood hazard map is a map of inundation area or depths at a certain level of flood, for instance, 1 in 100 years. And this map is useful for flood risk assessment and is also helpful for stakeholders and insurance service. However, because there is no observations of that, so the production of the flood hazard map is subject to multiple uncertainty sources. So in this study, we will assess the uncertainties from different sources, including the runoff input and also variance fitting distributions and also the variable in the flood frequency analysis. So this is the different uncertainty sources we are going to investigate it in this study. And what is need to say is the runoff is obtained from the Earth to observe WRR2, and there are 7 different kind of runoff driven by the same forcing but with different land surface model or the hydrological models. So this is the result of the global map, and we can see this is the mean flood water depth there is a special distribution of the water depths. We can see high water depths are found in the like Amazon and the southeast of China and Mekong rivers or the Ganges rivers. And the uncertainties are having the same special distribution of the water depths with higher uncertainty where the water depth is higher, but lower uncertainty in the places where water depth is lower. And for this is an example for Mekong River, and the result is for inundation area. We can see this is the general inundation area uncertainty with the mean values in the solid line and the shadow values at the uncertainty. But we can see the graphic, the panel B, there are actually two areas with the two variables. If the two are dividing too much, we will say that uncertainty is large, but we cannot see that the specific difference between these two means the uncertainty between the two variables is small. But for the runoff, there are 7 runoffs as said, and then we can see the mean values are separated among each runoff. So we can conclude that the uncertainty among these runoffs will be very large. And the last one is for the fitting distribution. Actually, when the flood is not too strong, the distributions are small, but during the extreme events, we can see large diversions between different fitting distributions, which means for these events, if we choose different fitting distribution, the result will be very different. And the last one is the result for different continents. We can see different colors representing different continents. And the red one is the Asia, and the Asia is suffering the largest population exposure and also GDP exposure to the floods. But the lower one is in other continents, and the top row is for the total values, and the lower is for the proportion. We can see for like this is Australian. And the US, they suffer lower risks of the flood. And then in different colors, there are different lines. We could say this is representing uncertainties from different runoff. And the blue one represents the Africa. And then they showed large diversions, which means in Africa, we have to care about the uncertainties due to data inefficiency of the model development. So this is all for the presentation. And if you have any questions, please join the discussion session. Thank you.
So good afternoon, everyone. So this is Mustajab from Kim Lab. So this poster is combined effort from our colleagues under Kim Sensei. So they are here on the top right side. So the poster is about the global potential of renewable energy resources, and mainly it is dealing about solar photovoltaics and wind energy. So globally, PV and wind energy has a huge potential to provide access to the cost-effective, secure, and environmentally sustainable supply of energy. So their rapid development, it has effect especially on the water sector, and also help minimizing the carbon footprints like global greenhouse gases emissions. So, but there are some factors like meteorological parameters and some decadal ocean atmospheric oscillations, which affect the potential of PV and wind energy resources respectively. So this study mainly deals about those kind of limitation factors. So in detail, so it mainly talks about that the future electricity demand is anticipated to reach around 50 terawatt by 2030. So currently there is just 15% input from the total, in the total there is just 15% input from the renewable energy resources, and talking about PV and wind energy, it further reduces to just 3%. So however, their potential is too much. So it is proposed like by 2050, so it can replace the conventional energy systems like we are using fossil fuels, etc. So such information is provided by National Renewable Energy Laboratory here for the solar energy and also the wind energy. So the left bottom figure shows the global potential of solar PV resources. So this global map shows that we have quite good potential around North America, Sub-Saharan Africa, Middle East, and parts of South Africa and Australia. So this right plot shows their variation, seasonal variation of potential along the latitude. So in this winter season, as shown with the red bar, we have the reduction from snow covers, and however other seasons, so we have plenty of these resources available. So this is calculated using the shortwave radiations, some performance ratio, which counts the reductions and the solar cell efficiency of 17%. And talking about wind, so we have mostly the potential available along the shore size. So this upper figure, it shows the ERA 5 reanalysis average wind power potential. So this is the potential for from 1979 to the 2020, and this bottom figure shows the wind speed, which is basically the main parameters to drive the wind potential. So it also uses the turbine area and some other parameters. So these two main resources, so they have the huge potential on existing the freshwater resources. So as shown by this bottom bar chart, so this uses the, bar chart shows the information about the global 17 regions, like if we use more energy from PV and wind. So this is basically about PV. However, so for wind, we can use similar kind of information. So for PV, so there is huge saving for, especially for China and USA, etc. For fresh water. So this kind of study will potentially contribute to the Sustainable Development Goal number 7, which is affordable and clean energy, and also decent work and economic growth goal number 8. So this is all from our side. Thank you very much.
Good afternoon, everyone. I am Debanjali Saha from Professor Kazuki Sensei's lab. Today, my presentation topic is improvement of disaster management approaches in Japan using paddy field. As we all know that Japan is a highly disaster-prone country where extreme disasters like Typhoon Hagibis in 2019 and Kyushu flood in 2020 can cause enormous losses. And the existing disaster management approaches may not be adequate if changed climate increases the frequency and intensity of such disasters. Therefore, sustainable and economically viable alternative approaches are essential. The paddy fields within the river basin can function as storage reservoir for floodwater generated by extreme rainfall during disasters, thus reducing flood risk in important areas. This study proposes the assessment of paddy fields' impact on flood risk reduction using a combined hydrologic water resource model and a river routing model. As you can see in the right figure, in the river basin, there are some green areas which indicate the paddy field area. So when the rainfall will fall in the river basin area, the water will be stored in this paddy field, and this is expected to reduce the discharge and inundation damages in the important downstream areas. So the main objective of my study will be to determine the changes in river discharge and inundation with paddy fields as inundation storage reservoir, and also do a cost-benefit analysis of the proposed technique in paddy cultivation. So this study is aimed for several major rivers of Japan, including Arakawa, Abukuma, Tone, Chikuma, etc. But such study can also be performed in river basins with similar geographical condition like Japan. So for my study, I will use several meteorological flow direction data and other parameters and boundary condition to the models. And for my study, I will be using the hydrological or water resources model HO8 to simulate the river discharge for with paddy field and without paddy field scenario. Then the inundation area and depth will be simulated using the river routing model Komaba. Afterwards, comparison of the two scenarios will provide differences in flood risk after using paddy field as storage reservoir. For base climatic events of this analysis, I will be using 2018 flood, 2019 typhoon, etc. So similar analysis can be performed using future climate data to assess the performance of the proposed flood management technique under changed climate as well. The HO8 model will be modified where the paddy field will be included additionally with existing 4 land types, and rainfall water is assumed to get stored within the conventional height of paddy field band, which is usually 25 to 30 centimeter in Japan. As of my initial findings, based on some calculations that I did from the last 2019 typhoon Hagibis, it is found that during typhoon, the contribution of paddy field in storing inundation water was significant. If we look at the total inundation area and the inundation area within the paddy field, then it is observed that the contribution of paddy field as an inundation storage reservoir is most of the cases around 80% or more. So for similar disaster, a good amount of water can be stored in the paddy field, which can reduce the peak river discharge and inundation area. So as of my ongoing and future work, the HO8 model simulation for different river basin areas for different climatic and field scenarios is ongoing. And using results from HO8, inundation depth and area generation using Komaba model is also what I plan to do after this HO8 model simulation. So if I move to the conclusion, using paddy field as a floodwater storage reservoir is less costly than the large-scale structural intervention needed sometimes. So assessing its impact with the combined hydrological and river routing model is a new approach in disaster management of Japan. Similar techniques are already being applied in some prefectures of Japan, but this kind of combined approach is new. And if this technique is effective and more profitable, then government organizations and end users can develop suitable plans to utilize the empty paddy fields for more sustainable disaster management. So that's it from my side. If you have any other question, please feel free to join the discussion. Thank you.